Okay, so we know what the correct color order is, right? It's just the colors of the rainbow. Roy G. Biv, ROYGBP, or Roy G. Biv if you're old. But why is it like that? How do we know that that's the right order? Well, you could look at a rainbow, but that doesn't actually help much. A rainbow is a spectrum, the colors blur together, and while any two sections are obviously different, finding a dividing line between the two adjacent colors is impossible. We see a blur of hue, not distinct patterns in a band of color. But here's another question. Rainbows commonly don't have pink or brown in them. There's no white, gray, black, gold, cyan, magenta, chartreuse, crimson, any of those other colors in Roy G. Biv. Where do they go? I want to talk about how we order colors, the methodologies and standards used, and why. Then maybe take a look at some alternatives, different ways of ordering colors, and the rationale behind each of those systems. But firstly, we have to start from the beginning. The mnemonic device Roy G. Biv traces its roots to Robert Boyle, a 17th century Irish Anglo-natural philosopher and one of the first chemists. In Experiments and Considerations Touching Colors, 1664, Robert Boyle compiled existing research into the nature of colors. While widely focused on chemical experiments involving color, it touched on things like colored beef, colored pigments, colored people, and colored light. Shining light through a prism, he described the spectrum that he produced as denoting the 5 consecution of colors: red, yellow, green, blue, and purple. This is notable for a few reasons. First, this work establishes Boyle as one of the first color theorists, and second, he makes a distinction between additive and subtractive coloration, which we'll discuss later. And third, he gives us a list of colors that is missing orange and indigo, 2 colors we English-speaking viewers normally recognize as their own thing. This is because of the work of Isaac Newton, who, besides being primarily known as a devout Christian, conducted some small scientific experiments with light a few years after Robert Boyle. His prism experiments yielded similar results, showing that refracted light, broken down into its component hues, could not be further distinguished in hue through further refraction. While he showed that combining the primary colors produced white when you blur them together, he did not, as some sources state, do so using a spinning color wheel. Newton, believing in the spiritual importance of the number 7, wanted to break the rainbow into 7 colors, and in his 1672 New Theory of Light and Color, added orange and indigo, coincidentally both being colors derived from plants used to make dye at that point in history. The 7 colors stuck around for the most part. However, we should note that Newton's blue was actually closer to what we would call cyan or light blue, where indigo was much more of the darker blue leading into the purple spectrum. So when people say that indigo and purple and blue are all too similar for the 3 colors to coexist, this is why they are like that. Newton's color wheel actually looked like this, partitioned in proportion with the wavelengths of the visual spectrum he determined from his experiments. Red, yellow, green, cyan/blue, and violet appeared to take the largest portions of the spectrum, giving us the 5 families of colored light. Okay, but here's another question. Why do rainbows look like rainbows? Rainbows form when light, most often sunlight, strikes vaporous water droplets or another refractive material, which redirects the light. An observer at the right angle can perceive these refractions as an arc of banded color, showing the full visible spectrum from red to violet. It's an arc because it's actually more of a rounded circle if you could see the full rainbow, because the material it's reflecting through is also like a circle. Primary rainbows are the most common, with red on the outermost, uppermost edge. But why is red first? Red has the lowest energy frequency of any colors in the visible spectrum, and just happens to end up on the top in the common form of refraction. Reddish frequencies occupy the largest portion of the visible spectrum of any color. In the primary rainbow, which is arguably the most common occurrence of all of the natural colors side by side, the larger, outer red band holds high contrast against the bluer sky. Purple and blue just kind of fade into the background and hard to see, so they don't draw as much attention. Additionally, many colors will read from top to bottom, and so process information in that order. All of this leads people to list red as first in most color orderings. However, this is not always how the rainbow forms. When light refracts multiple times inside of a water droplet that creates a rainbow, there is an additional effect that can occur where another secondary rainbow forms. This secondary rainbow reverses the color order, with violet at the outermost layer. However, these are less common, making them less influential in perception of the correct color order. Okay, so we've seen that Newton and Boyle are kind of arbitrarily dividing the visible color spectrum into divisions based on their own subjective interpretations of how many colors there should be. But how many colors are actually in a rainbow? Obviously, there are more than 7 colors in existence. You may be tempted to say that there are an infinite number of colors along the visible spectrum. However, this is wrong. There is actually a finite number, but it is functionally infinite. You see, light is a quantum phenomenon, and is composed of photons with finite energy levels. Each photon has a specific wavelength that it occupies that determines what color humans will register it as. So the real question we should be asking is, how many distinct frequencies can a photon have in the frequency range visible to humans? Because matter will reflect and absorb specific wavelengths based on its own unique properties, the materials that light passes through in order to form a rainbow is key. The sun, being a mass of incandescent plasma, emits an arbitrarily large number of photon frequencies, around 10 to the 45th power. However, that light has to pass through our eyes to be registered, so 10 to the 45th isn't the actual answer. This brings us to another tricky topic: the human eye. I am not an eye scientist, or an ientist, as you might say. My grasp of quantum mechanics and the behavior of the electromagnetic spectrum is purely theatrical, my grasp of biology limited to my hold on your mother's loins. I'll be relying on other people's explanations for this video to make any sort of sense. Luce Gilmore of Cambridge, UK says, "The retina has cones with 3 opsin pigments that are sensitive to different color bands, peaking in orangish red, green, and deep blue. However, in the retina, color information is encoded into red versus green and yellow versus blue channels for transmission into the optic cortex. Hence, the 4 basic colors of visual psychology are red, yellow, green, and blue." Break. Remember, we perceive color based on electrical signals relaying information to the brain, so that process determines how our brain will register visual appearances. Continuing. Cyan looks distinct from blue because both green and blue are firing in that band, so it appears brighter. Similarly, orange is towards the yellowish part of the red band where green cones are still firing strongly. Owing to the retinal encoding, the band we perceive as yellow is very narrow, whereas the red band is very broad. Also, violet appears reddish due to that encoding. Break. But now let's factor in light intensity. When cones detect color, our rods detect the overall light level. Because our eyes have 3 cones and the rods are capable of differentiating about 100 shades, humans with fully functioning eyes can detect about 100 to the 3rd power, or 1 million discernible colors. However, I've also seen estimates at around 10 million, but I haven't found the calculations for those, and those 2 magnitudes are close enough and large enough that the difference is negligible. It's important to note also the placement of our cones on the color spectrum. Blue, or short cones, are responsive to light in the 450 nanometer range, while red and green light, or mid and long cones, are much closer together at 540 and 570 nanometers. These placements are important because the responsive areas of each cone overlap to varying degrees, meaning that there are multiple ways of producing the same color cognition from different combinations of light spectra, like how yellow light can be replaced with a combination of red and green light, because how we detect yellow light is through red and green cones. Our brain sees it as the same. This brings us into a strange conversation about primary colors. Because aren't yellow, blue, and red supposed to be the primary colors? That's what all of my art teachers told me. Well, when talking about light, adding enough wavelengths of pure hue will eventually make a white light. White light contains the subfrequencies of all other colors. Light uses additive color. However, pigmented colors work differently. Pigments only reflect certain frequencies of light, absorbing all of the other ones that hit them. Seeing the color of a pigmented surface is seeing the colored light that it reflects back. When you mix different colored pigments, they end up absorbing most of the light, reflecting very little, which combines to make the color black. This is subtractive color. The primary additive colors are red, green, and blue because they're the frequencies attuned to the cones of our eyes. Mixing them creates yellow, cyan, and magenta. However, the primary subtractive colors are inverted because we're working in the opposite direction. Magenta, cyan, and yellow combine in subtractive colorations to make red, green, and blue. That's why your printer uses magenta, cyan, and yellow dye instead of red, green, and blue. Remember also that the retina encodes color in channels of red versus green, blue versus yellow, and black versus white. The red and green cones share more in common genetically than the blue cone, which is an odd man out. This has consequences in color blindness, which I could talk about, but won't. I can't tell for certain, but my best reading is the eye uses these three scales something like this. First, checking for levels of low wavelength versus high wavelength light, blue versus red and green, aka yellow, as well as a check of the overall light level, which would be the black versus white. Because the eye has different cones for red and green, an additional check is conducted to see if the light is closer to either red or green. This is why red, yellow, green, and blue are so prevalent in cognition as primary colors, rather than cyan and magenta, which are combinations of green and blue, which are further apart, and red and blue, which are even further apart. There's also the fact of magenta being more similar to an anti-green than a real color, being a cognitive compromise that distinguishes high levels of red and blue light from high levels of green light, because it has to do with the axes of the visible spectrum and color levels, and it's just too complicated to get into. Also, our black and white primary colors, they don't have hues and are more conditions of color and light level than actual primary components in themselves, but their impacts are so distinct that they deserve a sizable allotment of color space. My point is, the problem of a color ordering is that color isn't one-dimensional. It's not even two-dimensional. It's three-dimensional and not even symmetrical. Professor Albert Munsell published a color notation in 1905, a 3D representation of color space along three axioms: hue, or basic color, chroma, color intensity or saturation, and value, or lightness. His original segmented cylinder design allowed colors to be identified using these three aspects. In 1943, the Optical Society of America would publish a revised version of the Munsell color system, which relied on experimental data to more accurately determine unique swatches of color along those three axes. You may know a similar system by the HSV or HSL colors that you see in many art programs. All of this isn't even bringing up the CIE 1931 color space chromasticity diagram, which I don't even fully understand, but it doesn't look symmetrical or easy to explain. So basically, what optical science of the last few centuries has found is that color is most logically arranged as an amorphous blob of identifiable light spectra in coordinate space. Meaning, to include any colors beyond the hues, beyond those controlled for consistent value and saturation in a linear ordering of colors, is going to involve a degree of arbitrarity or inconsistency. But with all of the information I have gathered now heaped into a pile on your lap, I see no other route forward than to designate an ordering of my own subjectively objective opinion. So, what colors are we including? The Crayola website does have a registry of all 120 colors that they produce and recognize, but unfortunately, there is no official coloring order provided. Likely, they are too afraid to attempt to tackle this issue, as I so bravely have. However, I did find a helpful blog post that provides a complete list of those Crayola colors, arranged by their lowest numbered box order that they appear in, and an 11x11 grid, with hexadecimal and RGB codes. Well, the Crayola registry, or any other color list of that magnitude, has so many permutations that ordering it with any consistency is futile, unless you already have the list in hand. Plus, the result will have so many incongruencies that ordering it will be aesthetically unpleasant, which I think is what we're really after here. Just some aesthetic pleasure from an ordering that has a degree of rationale to it. The best choice may be to include one color from among each primary and secondary hue, and then a representative color for both the tints and the shades of that hue. something like this. That seems reasonable, right? But how do we order this? Assuming that we ignore the tones, start from the reds and work towards the violets, we could go left to right, or right to left, in each row, shifting up and down with tones for each hue. I don't like this, however, because while it is inclusive, it does create a disconnect for each new hue when we shift immediately from dark to light. Instead, we could do a snake-like pattern, connecting dark and light tones of adjacent hues. So pink into red, red into crimson, crimson into brown, brown into orange, orange into tan, tan into dandelion, etc. The problem is when we hit the collision of gold and forest, which really don't blend well together all that much. The more obvious bridge of the yellow-green divide is through line, and gold and brown blend together much better as well. There's a couple cases where the colors just won't line up well no matter which direction we start with. So I think the better solution is just to be more selective and exclude a few of the less novel colors, like crimson, forest, and dandelion, in favor of more common auxiliary colors, like gold, magenta, and brown. This lets us keep a larger array of tones while also being more congruent from hue to hue. Therefore, my revised ordering looks something more like this: pink, red, brown, orange, gold, yellow, lime green, cyan, blue, indigo, violet, magenta. With this ordering, we get to keep all of the colors in Roy G. Biv along primary subtractive colors like magenta and cyan, and also brown and pink and gold because I think they're neat. Please note the colors that I've shown here are all at full saturation, just changing in value of hue and value. But now what about the tones? Where do they go? Well, that depends. They obviously can't be placed just willy-nilly in the midst of the hues. That would be creating some fairly heavy incongruencies in our spectrum here. And they can't be separate either, white into gray into black. That's just how it goes. So either at the beginning or the end of the spectrum. If we want to keep the reds in the front of ordering, like the typical Roy G. Biv, then they should be at the end. However, magenta is a mid-tone here. It's not really closer to being black or white. And I don't want to place gray first because then there's no ridge between light and black, and it also doesn't really go well into magenta. We could try and jigger the front of the spectrum here so that brown comes before red. Brown, being a dark orange, is commonly associated with black. However, this means that we end up with an awkward front section where we shift from an orange hue into a red and then back to orange before going through the rest. And that doesn't feel good. Pink, however, has similar aesthetic relationships to white as brown and black, with pink being a lightish red. So in heresy to the red first philosophy, I would propose this ordering: black, gray, white, pink, red, brown, orange, gold, yellow, lime, green, cyan, blue, indigo, violet, magenta. Or Boogerp Orgulp Vivump. Is this more impractical to pronounce than Roy G. Biv? Yes, but not by much. Are these answers arbitrary to my own personal tastes? Yes, but it's my channel. Was this entire effort somewhat pointless and futile? Absolutely. Will I still rely on this sequence to put crayons in order next time I'm feeding the Titans in my fire team? 100%. No cap.